This is the video solution to problem 16-108. The problem reads, the mechanism produces intermittent motion of link AB. If the sprocket S is turning with an angular velocity of omega equals 6 radians per second, determine the angular velocity of link BC at this instant. The sprocket S is mounted on a shaft which is separate from a collinear shaft attached to link AB at point A. The pin at C is attached to one of the chain links. Alright, so just to reiterate what the problem statement says, it says the sprocket S is moving in a clockwise direction with omega equals 6 radians per second. And it also says that point C is moving vertically downward with the chain link. So point B and link BC will be moving, rotating about point C in a clockwise direction as well. Alright, so to begin, we're going to draw a free body diagram. And label the given information on the diagram. We know this is 30 degrees. This is 15 degrees. The length of BC is 0.15 meters. We know omega AB is given as 6 radians per second. And velocity at B will be perpendicular to link AB. We also know the velocity at C, again, is going to be straight down as it happens to follow the chain link. Alright. So we are asked to solve for the angular velocity of link BC. And we know this is going to equal the velocity at C divided by some perpendicular radius. That's the equation from kinematics. So we need to determine the velocity at C and this perpendicular radius. Now point C is just a point on the sprocket. So any point on the end of the sprocket at this instant will have the equation velocity equals omega times r. So at this instant, velocity equal 6 radians per second times 0.175 meters, the radius of the sprocket, and this is 1.05 meters per second, and as stated previously, it's in the down direction. Now we have to find this perpendicular radius, and to do that we are going to use an instant center method. So to find the instant center, we are going to draw two lines from both the velocity at B and the velocity at C, and these two lines are going to be perpendicular to both of these velocities. And where they intersect is the instant center. So we're going to call this distance from the instant center to point C RC to the IC, and this distance from point B to the IC, RB to the IC. Right. So we know only the length of BC. Now to find out the perpendicular radius we need for our equation here, we need to find RC to the instant center. So to do that, we're going to have to set this unknown radius in terms of the known length of BC. So to do that, we're going to do a bit of geometry and extend a line from point C to link AB such that it is perpendicular with link AB. And we're going to call this link D. Now, D equals RC to the IC sine of some angle. Now we know this angle here to be 30 degrees because the line connecting the incident center to point C is parallel to the horizontal axis at point A. And this equals 1.5 sine of the angle at point B. So we need to solve for this angle. Now we're given the 30 degrees at the incident center. So in order to solve for the angle at point B, we need to figure out what the angle is at point C. And we know that this angle here is just going to be 90 degrees plus 15 degrees, making this a total of 105 degrees. So the angle here up at point B is just 45 degrees. So we can come back down here and plug that in and solve for this distance, and it turns out to be 0.2121 meters. Alright, so now we have both unknowns and we can plug those into our equation. And we find that omega of BC equals 4.95 radians per second. And this is going, as stated before, in a clockwise direction. And this is the final answer to problem 16-108.